So I welcome you all to today's MateriAlZ seminar. So today we have the honor of hosting Professor Amit Misra from the University of Michigan. He's a department chair there in the Material Science and Engineering program in Ann Arbor. So he has previously worked at the Los Alamos National Lab, and he received his bachelor's degree in metallurgical engineering from BHU, Indian Institute. Now it's an Indian Institute of Technology, but he received it in 1989, so way back. And then after that, he went to University of Michigan in 1994, where he did his PhD. So incidentally, I and Amit actually studied at the same program at BHU in the metallurgical engineering. Probably may have been taught by the same professors. And although Amit is like 20 or 21 years senior to me. So Amit has mentored over 40 postdoctoral researchers and PhD students at Los Alamos and at the University of Michigan, and has received the Los Alamos Distinguished Postdoc Mentor Award. And he has co-authored over 350 peer-reviewed articles, and he's the principal editor of Materials Research Letters and chair of editorial board of MRS Bulletin. He has also been recognized as a fellow of AAAS and the Materials Research Society, ASM International, and the Los Alamos, and with the has a lot of awards under his name, such as the Brimacom Medalist and the MPMD Distinguished Scientist and the Distinguished Service Award from the same division. So the floor is all yours, Amit, and thanks for accepting our invite. And I'm looking forward to your seminar.
Thank you, Ankit and Krishna and organizers for the invitation. It's really great to present this talk to you virtually. Last time I visited ASU, I presented an in-person seminar, a slightly different topic. So these are my co-workers and collaborators listed here. Most of the work I will show will be the work done by these three PhD students, Ben, Yuche, and Bert Lien. Ben has recently graduated, and so has Yuche. Ben is now a postdoc at Los Alamos National Lab. Various parts of this research have been funded by either NSF or DOE. This talk will really be about microstructures. So although I'm using metals as an example, it's not so much about metals as such. It's more about how interface microstructures can lead to unique functionality. Coming from MSc department, I always put the work we are doing in the broader context that when you study engineered materials are the building blocks for all modern hardware-based technologies and sustainability for quality of life. And you can look at any high-tech product, you will be able to see the basis for that is some novel material and material functionality. And broadly, they'll fall into two categories: structural materials used for their mechanical properties, structures under load, applications in mechanical, aerospace, civil, nuclear, and so on, and functional materials used for physical, chemical, biological properties that can either be semiconductor, ceramics, inorganics for energy electronic applications, or can be organics, polymers, biomaterials for healthcare and consumer products and so on. So materials makes a broad impact. Structural materials, metals and alloys continues to be a hot topic of research for the new kinds of developments in the field. And you can just look around. If you just focus on the metallic alloy area, you will be able to see high-tech applications wherever the metals and coatings and alloys are used. And that requires new kinds of research all the way from electronics to nuclear to biomedical to space to transportation. All of these areas require lightweight, high strength, damage tolerant types of materials where microstructure and the role of microstructures becomes the key factor, which is the motivation for this kind of research. What are some of the scientific issues? One good way to bring yourself up to speed if you are not familiar is in any topical area of research, there are these basic research needs workshop reports that DOE, Office of Basic Energy Science, puts out. These are written by experts working in that field, academics that get together every few years or so. So the relevant reports to the research I'm doing will be these, but you can Google DOE BS workshop reports and it will take you to a site where in whatever area of research you are working on, you should be able to see what are the current hot topics of research and what are the fundamental scientific issues that are driving the kinds of research that DOE, BES, and NSF fund. So for metallic materials, it is things like how do you make structures that are strong and still lightweight? How do you make a hard matter heal damage or defects? And how do you make it resistant to failure under extreme conditions? So a lot of metallic alloys can easily be fabricated, but once you put it under extreme condition, high temperatures, radiation, or corrosive environment, then it can fail under unproductive kinds of situations. So there is still a lot of scientific basis that's needed to design microstructures for some kind of a tailored response that would enhance functionality in these kinds of extreme conditions. So this is my outline. There'll be a little bit of background on microstructures and mechanical behavior relationship, sort of strength of metals 101 type few slides. And I will get into talking a lot about hierarchical structures. So that will be my focus, different from some of the work I've presented before, made by physical vapor deposition in the form of thin films and coatings. And the second would be example of laser rapid solidification, which is relevant to additive manufacturing, where I will give examples of how to make nano hierarchical microstructures in aluminum-based eutectics. And since there are students joining, we'll also throw in some quizzes as we go along, just to make it fun and interesting, hopefully. So when we start with metal, so this is outside my office window. There is a metallic structure, 3 cubes, and I work in cubic metal, so I always look at and point to students. You can look at a macro structure on the surface of a metal, the way it is polished and prepared. But really what determines the property of a microstructure of a material is defined by things such as the grain size, the grain orientation. So this is a textbook type of a placeholder microstructure of a metal, where the different colors represent grain orientations, and this is a scale bar. So this is a microstructured material with grain size in the tens of micrometers regime. And by this model known as the Hall-Petch scaling law, it is known that the yield strength of this microstructure will scale with 1/square root of the average grain size. And so using that, we can get an idea of what the strength of a metal will be. This is an example for copper. If you plot the strength as 1/square root of the grain size, you get a linear relation with the slope of K, which is the Hall-Petch slope. And you get a sense of what the strength numbers will be. Typically on the order of a couple hundred megapascals, if the grain size is on the order of tens of micrometers, which is where most of the typical metallic microstructures are. And the reason for that is based on dislocation theory, that crystals deform by moving dislocations on crystallographic planes. And dislocations tend to pile up at grain boundaries because there is a crystallographic misorientation. And so the smaller the spacing between grain boundaries, the stronger the material becomes, because the grain boundaries are obstacles for shear or glide of dislocations. So using this kind of an idea, this has been used to refine microstructures to increase the strength. But of course, there are limits to what one can do with this. So I will give you an example with how you can have a composite microstructure. The previous one was a single phase microstructure, like a pure copper. In this case, you can create a layered, like a nanolaminate type of structure by layering 2 different materials. There could be both metals, or one could be metal, one could be a non-metal, and create a composite microstructure. So this is an example from copper niobium. Copper is face-centered cubic. Niobium is body-centered cubic. And you see this superlattice kind of structure that is formed by physical vapor deposition, where each individual layer can be controlled by deposition. So this is on the order of a nanometer, but we can, by deposition, make it to be whatever dimension we'd like. Now, the advantage of that is we get very strong materials, that when the spacing between interfaces or grain boundary gets down to a few nanometers, the strength level goes up beyond 1000 MPa. So if you remember, the previous slide showed an example where around 10 micrometer grain size was around 100 MPa. Once you get down to below 100 nanometer, the strength level gets up beyond the gigapascal barrier. And in copper-based materials, that is extremely high strength, because you can normalize it with the modulus, and you'll see that it's beginning to approach within a factor of 2 or 3 of what would be a lower bound estimate of the strength of a perfect dislocation-free crystal. So with this kind of an approach of making composite microstructures with finely spaced interfaces that block shear by dislocations, one can make super strong materials that are resistant to plastic deformation. Some of this you could also read in more detail in the recent MRS Bulletin January 2019 special issue. And going beyond the high strength, there have been many other properties that have been discovered by virtue of these interface boundaries. You can also suppress dislocation, cell structure formation, and obtain high fatigue strength. These boundaries can soak up point defects. They can attract, absorb, and annihilate point defects, resulting in materials that are resistant to radiation damage. You can also maintain the crystallography of the interface during plastic deformation, and extend these ideas to metallic glasses or ceramics that are sandwiched between nano layers of metals and get high strength and high deformability. So there has been a field of study looking at these kinds of laminate microstructures, where we are utilizing the nanoscale dimension as well as the properties of the interface. So one of the limitation now, so all that is good, but what's the limitation is that as this material becomes so strong, it also at the point of yield, so this is a 3 nanometer multilayer, this was deformed inside a transmission electron microscope in situ. And you saw that a shear band nucleated at the point of yield, creating a huge load drop, which means at the point of yield, when the layer thickness is only a few nanometers, we have dislocations sliding across the interface. So once plastic deformation starts, it localizes in the place where it starts. And that shear localization limits the ductility and the toughness. So to summarize this part, what we've known from the literature, from the work that's been done, is that you can create an AB where A and B can be 2 different metals or alloys, nanolaminate microstructure, get very high yield strength, but the strongest, which is the finest microstructures, lack a uniform deformation. They lack ductility and toughness because the mode of deformation becomes shear localization at yield. We also recognize that these kinds of nanocomposites have high interface area per unit volume. So we have to start to think of this microstructure in a different way. Instead of a size like a grain size or layer thickness, we have to think of it as microstructure that is interface dominated, because it's mostly interfaces, and the properties are going to be determined by this defect interface interaction, which means that there is need to be able to design these interfaces to enhance plasticity and toughness while maintaining high strength, which is a new direction of research in this field. So this is my first part, and at this point, I will throw in a quiz just for fun. So all the students who are listening, you can write down the answer in the chat. What is the #1 ranked job in the list of high-paying jobs for people who do not like stress, as compiled by MSN.com? This is just for fun, so hopefully while I get a sip of water, you can think of and write in the chat what you think the answer is.
So we have one response.
Okay, you can also Google it. And if you Google MSN.com, high-paying jobs for people who don't like stress, #1 is material scientist. So you could go read more about it and feel proud that you are a material scientist by this criterion. And this was released this year, that it ranked at the very top. This is something that we show to the students. So hopefully with that, you can be energized to stay awake for the rest of the presentation. So now I will talk about the next part. I introduced the idea of nanolaminate microstructure. I will now introduce this idea of hierarchical microstructure. So what do we mean by hierarchical? How is it made and what interesting properties does it have? And so to make that structure, we are going to use a different approach. Instead of doing a layer by layer deposition of A, B alternating, we are going to mix A and B together. So co-deposition, and do that at elevated temperatures and use elements that are immiscible. So A and B, such as I gave the example of copper, niobium, and similarly, there are many others. If you force these immiscible elements to mix at elevated temperature, there is instantaneous demixing. And that instantaneous demixing can produce other kinds of morphologies beyond just the regular laminate geometry that we get by sequential deposition. And the model systems that we will use in this will be copper as an example for FCC, and we will pair it with a body-centered cubic element that can be, I gave one example of niobium, that can be moly, tantalum, tungsten, chromium, vanadium, iron. All of these are body-centered cubic elements. Many of them are refractory elements. And the key is that all of these, if you look at the phase diagram of binary copper with iron or copper with moly or with niobium and so on, they are all immiscible and have positive heat of mixing. So there is no alloying and there is no intermetallic formation. You can take any binary pair and mix it at elevated temperature. It is going to demix instantaneously and create some kind of a morphological pattern. The question is, what kinds of morphological patterns do we get? How do we understand it? And what are some of the unique properties that we get from those morphologies? So this is work by Kumar Ankit, and he could probably give a seminar on his work on this phase field models of evolution of nanoscale morphologies during phase separation. The idea is that one can produce these different kinds of modulations. All of this is in the system copper and moly by co-mixing at elevated temperature and sputtering, where we get instantaneous demixing. So you can have vertical striations, or you can have lateral, or you can have random. And this is simply a competition between the rate of mixing, which is determined by the deposition rate, and the rate of demixing, which is determined by the interdiffusion. So at elevated temperatures, depending on the two elements, there is one element diffuses faster than the other. And so you'll see different kinds of patterns that evolve. All of these are nanoscale, and the shape changes. And the question would be, how do the properties change? And we see a very significant effect on compressive. This is all compression. I will show other tests later. On the morphology, for nominally the same length scales. It's not possible to have exactly same, but for nominally the same length scales, you see different morphologies have very different stress strain response and very different deformation modes. So the one at the top, the vertical concentration modulation, or the multi-layer structure, is what I showed before, the in situ deformation. Very high strength, but at the point of yield, it just fails by the shear localization. Because once you start pushing dislocations across and cutting across the interface, and you localize a shear band. So it is very hard, but does not propagate plasticity across. In the lateral concentration modulation, we see a behavior that is characterized by these kink bands. You form these kind of nano kink bands. So you get plasticity, but not much of strain hardening. Whereas in the random concentration modulation, which is like a bicontinuous intertwined morphology, two phases that are continuous all the way across. This is the case where we are able to spread plasticity all the way across the 3 dimensions. As a result of which, we are able to maintain plasticity across the material and not fail catastrophically. So there is promise in changing the shape and not just the size for a given material composition. Now, going beyond, the question we would ask is, how do you go from, so all of these that I showed, going from 1 dimension to 3 dimension, the length scale is still constant. So there is, you can define it by a shape, and you can define the microstructure by the composition modulation wavelength. But there is one concentration modulation wavelength that can define the length scale, the characteristic length scale of the microstructure. And the question was, can we introduce bimodal composite structures by deposition? Can you make it hierarchical? so that there is different length scales embedded inside, like many of the biological systems have, because that could in principle impart toughening in this kind of microstructure. And how do you do it? By deposition, and if you can, what kinds of properties do you get? Now, it turns out that purely by serendipity, my student was successful in discovering a structure that looked like this. And that has led to thinking about how to go back and make it by design. So I'll take a minute and describe to you this microstructure. It is hierarchical and it has many layers of complexity inside. So this is copper and moly that has been co-deposited at 400 degrees C. And with just two elements, we are seeing four phases. So there are two kinds of composites giving rise to a total of four phases. There is the composite that forms a matrix, which is the lighter structure that you see here, the lighter background. So this is Z contrast image. So the more moly-rich region is the matrix. And the matrix is shown by that pink square. If you blow it up, it actually has striations of this maize and blue striations of copper and moly-rich regions, where you have this lateral concentration modulation morphology, but copper is body-centered cubic. So in this case, copper takes on a metastable structure. It is body-centered cubic, lattice matched with the matrix body-centered cubic moly, and creating these kinds of phase-separated domains that make up the matrix. In the matrix are these discontinuous islands, these darker looking regions that's shown by that green box and blown up here. Those darker regions are copper rich. Copper is lighter than moly, so it appears darker, but it's not pure copper. If you blow it up, it actually, if you see here, the yellow matrix is the copper and the blue regions are moly rich. So those copper rich islands actually contain a superlattice of moly rich precipitates, which leads to these diffraction spots that account for the periodicity of those superlattice precipitates. And that is shown in this high resolution STEM image. Those brighter regions are moly atoms that have clustered in the form of an FCC structure. So moly-rich phase has become a face-centered cubic. It has precipitated inside the copper island, and it has formed a metastable structure. And also it has formed a periodic array in 3 dimensions to the point that you can pick up diffraction spots from the superlattice. All of this has happened by itself during deposition. There was no heat treatment done after deposition. The film is just growing, and when it's done, you take it out and cross-section and look at it, and you see this kind of structure. So what is making it do that, and how is this different? Which I don't have all the answers yet, but if you have ideas, and I would be happy to talk to you more later, and maybe there can be some collaboration. So we are trying to work on how to study this in more detail. One obvious question was that how does it depend on the temperature? Obviously, this does not form at room temperature, because at room temperature, you just don't have enough kinetics to have phase separation. But if you increase the deposition temperature, does this structure go away, or is it stable? So we increase the deposition temperature. I will skip that schematic and show you what it looks like at 600 degrees C. The structure is maintained, so it still has these hierarchical structure. There's a matrix, and if you blow up the matrix, you see these lateral concentration stripes, very fine scale, about 5 to 10 nanometer composition modulation wavelength. The difference is that at 600 degrees C, copper has now transformed to its equilibrium structure. It's become face-centered cubic, while moly, which is the brighter stripes, is body-centered cubic. So that defines the matrix. And in that composite matrix are these islands that are randomly distributed. And inside those islands, we have moly precipitates. And moly precipitates are still face-centered cubic. So this is, you can see the size has now increased a little bit. It's approaching 2 nanometer, but it's still maintaining coherency. It's still FCC. It is no longer forming the 3-dimensional superlattice array. It's more of a linear array. So you can see those white lines. Those are actually dots of moly precipitates that are linear, that have lined up along certain directions inside that island. So clearly there is structure forming inside structure. There is first kind of phase separation, then there is phase separation inside that, and there is a different kind of phase separation inside the other domain. So very bizarre and interesting kind of morphology that is forming during deposition. So if you go even higher to 800 degrees C, which is extremely high temperature for copper, not so much for moly. So you'll see again that structure is maintained. So in this case, you'll see the structure is getting coarser. So you'll see the matrix structure is the copper and moly. So this is slightly coarser, but there's not much difference. Copper is already FCC from 600 degrees C, and that is maintained here. But inside those copper-rich islands, there are moly, these stringers that are actually arrays of these moly precipitates. And what is interesting is that there's a bimodal distribution of precipitates. You still see some FCC moly precipitates. The sizes have increased up to a little less than a 5 nanometer or so. But a lot of the moly precipitates have now become BCC. So at 800 degrees C, those have coarsened and transformed from the metastable FCC to the equilibrium BCC structure of moly. And they don't have the three-dimensional superlattice, but they do have the linear arrays that are forming. So it is sort of structure inside structure in the nanocomposite inside nanocomposite. So very interesting structures. The question is, what are the properties? So first looking at the compression, so that's the 3 nanometer that I showed before, the multi-layer structure. Hierarchical structure has a very pronounced elastic plastic type of transition because the two composites deform in different ways. The copper islands that have those nano dots of moly, they have a characteristic stress strain response. The matrix that has the face separated copper moly has a different stress strain response. And what we are seeing is a composite of those two. So you're seeing where you go from elastic behavior to elastic plastic transition, and then finally to yield. So very high strain hardening rate, which has been lacking in the regular multi-layer structure. So by getting a very high strain hardening rate, we are able to get uniform distribution in plasticity from that shear localization to more uniform distribution and plasticity in small scale. So these are, we've also done tension tests. So we can do a fib lift out and do a tension test inside a transmission electron microscope. So you can measure the stress strain response of the two different composites inside that hierarchical structure. So this is the copper domain with nano moly precipitates. It has higher plasticity. So you can see that most of the plasticity is coming from these relatively softer regions. It is still pretty hard compared to pure copper. Whereas the moly-rich nanoscale, which is very fine scale, behaves more like the multi-layer, which is very high strength, but uniform elongation. But together, they are able to produce a much better composite response of strength and deformation. Okay. So all of this was just uniaxial compression and then tension. One of the tests that was missing was a test that would measure some kind of a crack growth response. It's difficult to do in thin films. So we, in collaboration with a group at Los Alamos, we have done these kinds of bend tests where you grow film thicker about up to 5 microns, and then we can make this kind of a 3-point bend test, create a very sharp notch, and then do a bend test inside in situ in SEM. So this is a bend test in situ for a multi-layers, and you'll see that as soon as the crack formed at the notch, just in one frame, the sample just fractured. There was no crack growth resistance. As soon as the crack popped, it just failed in one frame. How is this different when you have the, go to the next slide here. Yeah, so this is the hierarchical structure. You will see a very different response here. You can see it right away that it is giving the indication of significantly enhanced crack growth resistance. The crack has popped, but the sample did not fail. The crack was able to meander, but we were able to preserve that sample and then section this and look at it in TEM. So we are able to do a fib lift out and look at it in TEM. We can also, there are expressions, these kinds of tests have been done for silicon microbeams of silicon, and there are expressions that others have derived where you can, from these tests, because the test is done in situ, you can measure the crack opening displacement. And we know the yield strength, so we can estimate what the J integral will be, the strain energy release rate, which is maybe a better descriptor than the K1 because we have so much plasticity at the crack tip. So we are able to plot the J integral as a function of the crack length in this case. For the case of multilayer, there is just one dot because the sample failed as soon as the crack formed. So there is no resistance, there is no R curve behavior. The resistance does not increase as the crack length increases. But for the case of the hierarchical microstructure, there's a significant increase in the strain energy release as the crack propagates across. That had never been shown for these kinds of very fine scale multilayers. So it's very promising. Of course, there's some scatter depending on how you measure the yield strength, but it is very promising to see this kind of a crack growth resistance. Now, we were able to, from that in situ test, because the sample was intact, to section and do a fib lift out and observe the crack tip inside a TEM. So this is now a STEM image of the crack tip. And you can see that hierarchical structure, the matrix where you see very fine scale striations, the darker regions are copper rich, which have those moly precipitates that almost look linear, but that's just a row of moly precipitates. And you can see all kinds of toughening mechanisms. There is crack bridging, there is deflection along the copper moly interface, and there's significant plasticity and crack meandering. So by virtue of having this kind of a complex hierarchical microstructure, all of it inside a nanoscale domain, we are able to see a significant crack growth resistance inside these materials, so which is very promising and opportunity for further research. So this section of the talk I will summarize to say that we have gone from the old work, which was sequential deposition to make multi-layer structure, to co-deposition, where you could create something that looks like multi-layer by vertical concentration modulation, or have other morphologies. Random concentration modulation is the best of these three because it provides more uniform plasticity while still preserving strength. But all of these do not increase the toughness so much. By the time when the lambda gets down to a few nanometer, there's limited microstructure designed to enhance toughness. And that required a very different kind of microstructure design, where we, by luck, actually discovered this, and now we can now go back and study in more detail. The hierarchical structure is more promising in enhancing toughness in these structures. So this completes my second part, and before I go to the next part, there is one more quiz that I'll throw in. So all of you, faculty and students, maybe you know about this. I was thinking of what is common between Arizona and Ann Arbor, besides Steve Cross, who went from Michigan to Arizona. So here's a question: which top 10 list by Wallet Hub and CNB, published in CNBC.com, features both Scottsdale, Arizona and Ann Arbor, Michigan? And actually it also lists Tempe, Arizona. So feel free to write it in the chat. This is just for fun. Maybe you know it.
Looks like a difficult one.
Just like a difficult one. So we'll go to the next. This is the 10 best college towns of 2019. And they have defined college town, the quality of college town, by factors such as cost, social environment, like having a life, and academic and economic opportunities. And of course, college towns can be large cities, like population greater than 300,000, or medium size, like less than 300,000, but more than 125,000. So this is where you see Scottsdale and Tempe, both there. And smaller towns like Ann Arbor is in this list of towns less than 125,000. So again, something that often university students may not know, but it's very important to be living in a town where you have more than just academics. There are economic opportunities, and it's an affordable place to live, as well as there is social life in that area. So it's very good to see that. Again, something that's common between the two campuses. Final thing, I'll make a change from vapor deposition. So vapor deposition is fine for thin films, for applications might be in coatings. But what about bulk structures? And can you get microstructure design kind of similar to what I just showed using bulk-like microstructure types of processing? So this is an approach that we are, again, starting with things that naturally form two-phase structures. That's the starting point. In the case of copper BCC, we picked immiscible systems. In this case, we are picking from phase diagram systems that are eutectics. So eutectic meaning that from a liquid phase, you form two solid phases simultaneously. Aluminum silicon is a very simple textbook example that we teach in undergraduate class. Aluminum copper is another very simple textbook example, very well-known eutectic systems. What if you make it by laser melting, where you get very high cooling rates? There has been work done in 1980s and 90s where they showed you can get very fine scale structures in these eutectics. But back in those days, we could not do a lot of these in situ nanomechanics and could not study the mechanical behavior and be able to understand how to control microstructures. So this is an area that is very active in research, and I will show you one very simple example. So most of the undergraduate material science courses will introduce phase diagram, and one of the best, most common examples is aluminum silicon. The easiest phase diagram you can think of, eutectic. Aluminum and silicon do not mix. At room temperature, there is minimal silicon alloying in aluminum, and there's a eutectic at about 12.6%. And this eutectic has this discontinuous structure of silicon. It says plates here, actually it is more flake type structure. You see these discontinuous flakes that form. The scale is 50 micrometer. So very coarse structure, not very useful, not very high strength. If you go on the silicon rich side, so you get hyper eutectic structure. So first silicon phase will form. So you see here those large dark regions, very coarse, very brittle silicon, and in between the remaining liquid will then solidify as by this eutectic reaction of almost pure aluminum and almost pure silicon. Essentially pure silicon, very fine scale structure that can form here. But still fine scale meaning maybe 10 micron or so in that range. What happens under laser is that the cooling rates can be thousands to 10,000 Kelvin per second, and the structure completely changes. So this is a cross section of a laser melt pool where you see heterogeneous structure starts to form. The interesting thing is the composition does not change. So we started with a hyper eutectic, 20% silicon, realizing there might be some silicon loss because of vaporization and so on. And the goal was to produce something that is closer to eutectic structure. And you see at the bottom of the melt pool where the structure did not melt, you can see the textbook style of eutectic structure with silicon flakes. Inside the melt pool, which is everything inside the dotted semicircle, the structure has become so fine that you cannot resolve it with this micron at this resolution of 20 micron. But if you blow it up, you can see two different kinds of structures that are shown here. One that looks a two-phase where you have the silicon fiber-looking morphology, and that scale is now 200 nanometer. So you get about like 50 nanometer fibers, very fine scale, and also different shape. And you get this other kind where you have these aluminum dendrites, and the remaining structure is the eutectic. We can go further and look inside to see the structure is very surprising. That is not just fine scale and different shape from flake to fibers of silicon. You have these domains or colonies, so it's not single crystal, but within these domains or grains or colonies, you have a regular eutectic structure. What's also surprising is that if you look inside those silicon fibers that are looking like they're interconnected, you see these faults, you see these dark lines inside those silicon fibers. And when you do high resolution imaging and diffraction, it turns out a lot of these are stacking faults and twins. So inside the silicon fiber, it's actually, as it is growing from a liquid phase in the eutectic, the silicon fibers are not defect free. They're actually growing in this twin structure. So you have, this is a silicon fiber. Inside you see these planar contrast from these planar defects that are full of these stacking faults and twins. So we have created a nano-twinned and faulted silicon fiber inside the eutectic matrix, inside that laser zone, creating a hierarchy of defects in that very simple composition. In the other one, where you get this two-phase structure where you have eutectic with the primary aluminum, notice that this looks like a hypo-eutectic, which is you form primary aluminum, even though the composition is hyper-eutectic. And that's just an effect of far from equilibrium solidification. Very rapid quenching can do that. It can change what you would expect from an equilibrium phase diagram. But what's interesting is that sometimes inside those aluminum dendrites, you start to see these fine precipitates. Those turn out to be silicon precipitates. So we have only two elements, aluminum and silicon, so that's what will form. So you get silicon forming as these fine precipitates. So this is beginning to look like the structure I showed for copper moly, formed under very different kind of processing conditions, but it is hierarchical in nature. So you have these, a matrix defined by a eutectic structure, in this case of aluminum silicon fibers, where silicon fiber itself is nano-twinned, and having these islands of these coarse aluminum dendrites that internally contain silicon precipitation. So this is just showing that you have silicon precipitates. So just to summarize, from the same composition, that's the key point. We did not change composition. There's maybe a subtle change in the cooling rate in terms of where we saw the structure with respect to the free surface. Maybe some of these are forming at a higher cooling rate than the other, but this is very different from the regular eutectic structure that you will form under melting. This is different in many ways. One is that silicon shape has changed. It has become fiber. Second is very fine. The very fine part was expected. The part that was surprising was the nano-twin structure and the fact that in aluminum dendrite, you see these very fine silicon precipitates. What does that do to the properties? I will only show the compression. We are doing tension and we'll do other tests, but it's very interesting that if you compare with the regular aluminum silicon, the textbook eutectic structure, it has very low strength, about 200 or so MPa. And even in compression, you don't get much plasticity in it because silicon flakes that are tens of microns are brittle and there is no plastic compatibility. So you get brittle fracture, limited deformation, even in compression. But what's happened under these kinds of structures, so the three microstructures that I showed in the previous slide that are shown here in the schematics, and the red box shows the fully eutectic with nano-twin silicon fibers. That's the best behavior we are seeing, the strongest material, but also high strain hardening rate, which leads to stable plastic flow. I think that's the key part, as you see in this slide, that shows the strain hardening rate is very high, that prevents flow localization. It prevents strain from localizing at the onset of yield. So the entire sample can begin to yield. The heterogeneous structures are a bit weaker because, as you would expect, the aluminum dendrites will have lower strength. But in compression, we are not able to tell the difference between the true plasticity. So we are doing tension tests to study that. So again, this is very promising, and this is just showing when you compare the behavior in compression, the ASCAS, so this was not laser refined, showed these brittle cracks that form during compression, and right at the point of silicon flake where aluminum is plastically deforming but silicon is not, and that leads to the failure. But under heterogeneous or fully eutectic structure, especially fully eutectic, you see signs of more uniform deformation. In the case of these heterogeneous, you see some signs of where on the surface you have the aluminum dendrites, those are deforming more, so they see some extrusion on the surface there. But generally there is, for the fully eutectic, the homogeneity of plasticity increases with the heterogeneity of microstructure. So that's the punchline of this, and that's the surprising behavior, that by making the structure more heterogeneous, we are making plastic flow more homogeneous at very high strength levels. Similar behavior seen in the other eutectic of aluminum to copper, where this is more surprising because aluminum to copper is a tetragonal structure. What is in the tetragonal is not cubic. Silicon at least is cubic. And here also we see something similar, that as the structure gets finer, not only it is stronger, you get more plasticity, but more importantly, the distribution of plasticity that you can see from these very fine scale slip bands that are distributed uniformly. The plasticity gets distributed uniformly, and that is very promising, that it is suppressing these kinds of localization that we often see as the bottleneck with these high strength nanomaterials. So this brings me to the summary of this part to show that these kinds of laser refined structures that have been known in the literature to have fine scale structures by laser melting. What is new is that by doing these nanomechanical tests, and especially doing in situ, we are able to see that the increased microstructural heterogeneity at nanoscale enhances the homogeneity of plastic flow while maintaining the very high strength. In fact, you can increase the strength and you can increase the plasticity because you are able to somehow make the hard phase co-deform with the soft phase, as well as increase the strain hardening rate. So with that, I think this is my last slide. I'm going to stop and say that microstructures are the key. And I think regardless of what kinds of materials you are studying, the properties are driven by the microstructures and the defect microstructures going way beyond the chemical composition. And even with the same chemical composition, we can change the microstructure that traditionally has been studied primarily by a single parameter such as grain size or with texture. We can now begin to bring in the shape and the multitude of shapes and the hierarchy of interfaces and the defect structures, which is again a very promising area for material science in this field. And we have shown these with different processing techniques. I only talked about PVD and direct metal deposition. It has also been seen in severe plastic deformation, which I did not have time to talk about. So I will stop there and see if you have any questions or if there are any discussion point that you want to. I think we have a few minutes left, I believe. Thank you very much for your attention.
Yeah, thank you, Amit. That was a really nice talk. I learned a few things as well. So now I would like to invite questions. I don't have any questions in the chat box, but then please keep them coming. So first question I have received is from Ankita Roy. So Ankita, can you unmute yourself and ask the question?
Hi, Professor. I really love the talk. I just wanted to ask you, like in the hierarchical and in the random structure, how do you measure the K1C? Because K1C is the one you showed is sigma y is pertaining to a particular metal. So if you don't know how the structure is changing, I mean when it's moving from one material to the other, so how do you measure the K1C of the or the strain energy release rate overall of the material?
So a good point. So what we do is we do the tension test from fib lift out that I showed in one slide. So we measure the yield strength of that microstructure. We measure the yield strength of the hierarchical microstructure without the notch. So that's what that sigma y is meant to be in that equation. Okay. And we have measured it both by compression and by tension. Ideally, it should be by tension, but with tension, sometimes you get more scatter. And so we did with compression also to compare just to see how much difference you get. And I showed in that plot that with compression, you get slightly higher because with tension, sometimes you get fracture before yield. But your question is very good that you have to know the yield strength of this, the microstructure that we are seeing on this slide. You have to know the yield strength of this microstructure to be able to know the fracture toughness once you measure the crack opening displacement from those tests.
So Professor, one more question. Are we tracing when we are moving from one microstructure, I mean one layer to the other? Like, is there any way of tracing if we are doing the vertically stacked one or the horizontally stacked one or the random one?
Yes, I think that,
computationally, can we do that? Like, are we doing that?
Computationally is a very good question. I have asked my collaborators to work on it. They have to create a model in the computer, but yes, that has not been done. But yes, we are tracing it because the test is in situ. So let me go back here. This is the in situ test. Now, the way this surface is prepared, so this is as fib cut. So in this case, we don't see the contrast from the two structures. So if I play that movie again, you'll see the crack will form, and you'll see the crack is not able to propagate. It will just jump from here and there. It shows the structure is tough, but it is not able to show, I think, exactly what you are asking is, can you track that is going from one composite to the other? Because I don't see the contrast here on this image in situ when we are doing the test. So what we do is then when the test has stopped, because the sample did not fail, we section this with fib and take the foil out and put it in TEM. And so that is shown in the next slide here. So here, so this is one way where we can track it. So this is how the crack progressed. And you can see as it is going from one microstructure to the other, how the crack opening is changed. And from here, you can discern what the possible strain energy release mechanisms are. That you see more crack bridging from the relatively more ductile copper island phase, and where there's some crack deflection along the interface also, copper moly interface. And crack was able to jump from here to there. But for what is needed is that for each of these, we have to compute to understand which is more important. We have to find a way to compute that each unit process and then do this full simulation if we can. This will be very exciting for someone to do, but my collaborators are working on that. But a very, very good question, very insightful.
Thanks a lot.
Okay, so the next question is from Jagan. Yes, Jagan, go ahead.
Very interesting talk. I had a quick question about actually two questions actually. One is when you looked at the aluminum silicon detectives, the microstructure where you had the silicon particles within the aluminum kind of blob, so to speak, it seemed to have a slightly lower strength than the other one, which doesn't have this, right? And that is kind of surprising, isn't it?
Yeah, so that's a good point that we are trying to analyze that in more detail to get more statistics. The initial thinking is that those silicon particles in the samples that we tested were coarse. And so we think they are not doing much in terms of precipitation hardening. And so that's within the, I would say, scatter range for doing these tests. So we have to find a way to make those silicon precipitates finer. We just don't know how, in terms of what knob do you turn in the processing, because the hypothesis is that in the primary aluminum dendrite that formed, some silicon was trapped, and because silicon is not soluble, so it precipitated inside. And so if you could control that somehow, it may not be possible. Maybe with laser we are working on, there's no science behind how to do it. So they are doing it empirically in terms of how do you change the scan speed and how do you change the power and the spot size to be able to get down to this level of microstructure. But again, yeah.
That is kind of more general. It's like how stable are these microstructures, right? You can make them, and how do they respond to stress or like temperature changes and so on?
Yeah. So which one? The aluminum silicon?
All of them actually. The ones that we showed for copper molybdenum all the way to this thing, right? Some of the CO copper moly stuff is deposited at high temperatures, so you would have expected that they will probably remain stable.
Yep.
But these aluminum silicon eutectics that you laser emit, like how stable are those?
Very, very good point. I think I agree with you that the copper moly should be stable up to the temperature at which it was deposited, because it's slow deposition, and we have done some long deposition and see the structure remains the same. The aluminum silicon we have not done, and that I think is an area for research, because there is a lot of interest for using this commercial interest for aluminum alloys for hot applications and vehicle technologies. And hot there means 300 degrees C to 500 degrees C, the cast aluminum that's used in automotive engine and so on. And I think there is ways, if you can, generally the answer, my guess is it will not be very stable. That would be my guess. If we take it up to 300, 400 degrees C, the structure will coarsen. But we need data to understand how rapidly, and we need ways to make it more stable, because if you can, right now the applications will be in room temperature, but if you want to have applications at elevated temperature for aluminum, there's a lot of promise, but we may have to find maybe some other alloying elements to make it stable at elevated temperature. But I think it's opened up that kind of area.
Okay.
Thank you for your question.
Okay, so thank you, Jagan. So the next question is from Wataru Takeda. So can you unmute yourself and ask the question, or otherwise we can just read the
Yes. Yes. Hi. So my question is really the experimental specific. So I have a question about TM measurement that you've done. I saw lots of beautiful pictures. And so what was the thickness of your samples?
I think generally would be less than 100 nanometer would be my guess.
Okay.
But
And
we did not. I saw your question. We don't see evidence of any amorphization.
okay. And did you use bright field or dark field to identify the different grains?
So we have used all kinds of imaging. A lot of what works is the Z contrast imaging. So high angular dark field to see composition contrast, and then high resolution imaging, and the HADF images have been very helpful.
Okay, thank you.
All right. So the next question is from Rahul. Yes, Rahul, go ahead, unmute yourself and ask the question.
Yeah, this is a great talk. Thank you very much for it. So my question was that, so typically it appears that with the laser, surface treatment, it seems like this would be a replacement for, say, applying a film on the surface. So instead of, coating something with the material that is stronger, you would just modify the surface with this laser treatment to make it, structurally more sound. So my question was, have you considered just instead pulsing a lamellar or layered non-hierarchical film with laser to see if it reintegrates into a hierarchical structure? Just to see if something that is already decomposed can again reintegrate into something hierarchical.
Yeah, that's a good question. Yeah, we have not done that to see how you can change morphologies by subsequent laser treatment of different kinds of pulses. Very good question. Yeah, I think that's also an area of research. And with regard to, again, a lot of, as I said in the beginning, this is funded by basic energy science and NSF. So it's all very basic science. In terms of application, it can be applied in many ways. They do laser cladding, they're also doing with powders. They can deposit a surface layer and create, they just have to learn to understand the microstructure better in terms of what they'll get. There are many ways in which we can do surface treatment with laser, or you can do deposit a layer, and there are a lot of different things they can do, where I think it will have more short-term applications.
Okay, so thank you, Rahul. So are there any other questions?
I just had a very brief question. Do you, Amit, do you think we can see inverse Hall pitch effect in metals?
I have not seen it. I mean, others maybe have seen it, but we have not. I mean, we see if you define Hall pitch strictly as 1 over square root, so that 1 over square root scaling law tends to break down. The strengthening continues. The scaling law changes, but then you reach some kind of saturation. Below that, what you see are subject to interpretation. So generally, if the material is high quality and you maintain the morphology that you have, then I think you should not expect to see an inverse Hall pitch. So wherever people have seen inverse Hall pitch, there was some other kind of instability.
Okay.
Either contamination or amorphous layer at boundaries or something else. They went down so fine that something else changed.
Okay.
And maybe Jagan has experience also. I mean, sometimes you'll see grain growth during a test, and there can be other things. You can see reversible plasticity. A lot of things can happen when you have very fine scale pure metals. Especially when you have composite metals, there's less chance, because the real interface is a boundary between, say, copper versus a refractory metal. And if that, as long as that is pure and it's not amorphous or something, then it should be resisting deformation.
Okay.
There is, I don't know, along those lines, there has been, just I think last week, there was a paper in Science from K. Lu's group where they've discovered a new kind of very interesting nano copper, which is pure copper, and it is stable, 5 nanometer grain or something. It's stable up to melting point or something. I will send you that. I was reading it. Very intriguing structure, the way they have overcome this issue that a lot of people had of when you get down very fine, it'll become unstable.
Okay, and I had to take a quick call. When you were discussing the silicon, aluminum silicon, so you said that in the silicon you were seeing twinning.
Yeah.
And on load application or release, is there a chance of detwinning in silicon at all that could lead to?
So this is twinning from growth. It's not from deformation.
Okay, so it's not, it's a growth twin. Okay.
Yeah, so this is when silicon fibers grow from liquid phase, this is how it is growing.
Okay.
Twins in silicon have also been seen in nanowires. So if you talk to electronic materials people who grow nanowires of silicon, so they also seen from the vapor phase. And sometimes the silicon nanowires, they grow it from a gold silicon eutectic. They have a melt pool and they drag it and grow. So this is just growth twins. What happens under deformation, we don't know yet. So we have to see if you get deformation twins or not.
Cool. Thanks, Amit. This was great. I think lots of people have logged off. I think there were like 58 and now it's dwindled to 22 because we have a class at 12 p.m. So I think lots of the grad students, at least at UFA, have left for that class. But I mean, I keep saying this to every speaker. We actually have a polo that we want to ship to all our speakers with our MateriAlZ logo, and we haven't done that, and we will definitely do that this week. Elsa, are you online? Anyway, sorry about that. Ankit, we'll definitely ship it. Our idea was for all speakers to wear that during their talk.
During the talk, okay.
But I have rarely ventured out of my home. So going to the post office is too a big task for me. Like I need to stand in line. I don't want to do that.
We will do that soon, and maybe in the next year also we can actually have this up and running where the presenters can actually wear the polos and then present.
Yeah, you can think of sending it virtually, like an image, and ask the speakers to use that as the background banner.
Right. So we still have one more question from Truman. So Truman, can you unmute yourself and ask the question?
Yeah. Hi. Thank you for the great talk. I was wondering if you could switch back to that slide you had of the melt pool and the tensile stress. I think it was 46. 45. I was wondering if there had been, so within that melt pool region that you show there, I was wondering if there was any pattern in where these different phases are appearing and whether there's been an effort to measure the distribution of each phase within that melt pool region.
Yeah, that's a good question. That's exactly what we are working on now. So we are going back and characterizing a lot more of these melt pools under different conditions to understand why you get these different morphologies. We have been able to nail it down that there are 3 distinct morphologies. And it seems the fully eutectic, which is shown in that red box, is in the middle part or lower part of that pool, where the cooling rate might be slightly lower. And near surface, you'll see more of the hierarchical structure with the aluminum dendrites. When we get those silicon precipitates, it's still not known. I think somehow that there's a lot more work to be done to relate the structure to the property, but also relate the structure to the processing. Because we don't know the cooling rate, I think. So we can't measure the cooling rate. So they are doing calculations of the cooling rate in the melt pool. So there's a lot more work to be done there. So thank you for your question.
Thank you.
So we don't have any more questions coming. So let me just ask one last question, a topic I've been interested in all this way through. So Amit, I think I've asked you this question, but let me just put this question in a slightly different manner. So I was always very fascinated about the substructuring that goes on in copper. So you have got these copper-rich islands and you have got the moly, which sort of self-assembles into a substructure. So do you think that this will change if we were to talk about a more conventional system like copper nickel, where both crystal structures are FCC and FCC? and that can actually undergo spinodal decomposition as opposed to, it's not immiscible, but it's actually spinodal decomposition.
Yeah, depends if you can get a majority phase. I think what's happening in the island is that they're copper rich, and whatever moly is trapped is a minority phase. And I'm guessing minority might be 10% or so, and so it cannot form the stripe pattern, so it's forming these dots.
Yeah.
So if you can find that kind of composition, then it should be possible in any spinodal.
Okay. So it occurs at a very asymmetric composition. That's what.
Yeah, exactly. I think that's the idea, that if it is asymmetric, then you can have this kind of, but why is it so regular? And then why it goes from this to the linear? So you have these dots that are lining up. It forms a linear. When does it form a linear row of dots versus a three-dimensional arrangement of those precipitates? And those are also different kinds of spinodal inside.
So at the length scale is not something that a phase field simulation would predict. Like this is a atomistic scale defect or substructuring that you're looking at. So do you think a method like KMC or I don't know, phase field crystal would work much better in this context?
It could be, yeah. Although phase field could be tried independent of length scale, just to see how the morphology will change if you had different composition. If it was not equiatomic, if it was asymmetric, then what kind of pattern will form? You can even create an alloy and then age it or heat treat it. It doesn't have to be following the what is happening in deposition. So we think what's happening in deposition is that it's a two-step process. In the first step, you create the moly-rich matrix and those copper-rich islands. And then as deposition continues, then there is maybe further microstructure evolution inside those separated domains. So it may be possible to take a copper grain, mix some percent of moly in it, 5 or 10% homogeneously, and then run a phase field to see how that evolves.
Okay. Yeah.
Independent of length scale, to see what you get.
Yeah, right. Yeah.
But a lot of these things have not been studied because they were not observed in these vapor deposited films.
Yeah, yeah. Certainly, like the kinetics that comes in with the deposition of a layer alters a lot of things because things are highly out of equilibrium. Whereas when you take a block and just anneal it with some moly mixed, it will be closer to equilibrium. It will have time to relax and fuse. So that's an interesting comparison. Yes.
Yeah.
All right. Yeah. So thank you for the talk. And
thank you.
We're honored to host you today. And
thanks a lot, Amit.
Thank you, everybody. Take care. See you sometime. Yeah.
Yep.
Okay. Bye.
Bye.